All right, okay. So, hi, I'm Raya, and I'm going to be taking a class on trigonometry today. I know this is very controversial, and yeah, I was getting a lot of DMs asking me not to do trig, but IUChem is coming closer, and we should really be doing trig now just to practice. So, yeah, I mean, uh, like most of the people today who joined are pretty new. I've never seen you guys. So I'll tell you a few things before I start. That is, the first thing is that trig is like very computational. And for some problems, I'll be just telling you how to do the problem and not show the complete computation. But for the properties and theorems that we're going to do, I want to do rigorous proofs because I think that proofs for the theorems are pretty important at this point. So I'll be doing that. And in case you guys are familiar with these problems, I'll share some buffer problems that you can try. And another thing that I wanted to mention is that if you have seen a problem before and have done a problem before, or if you've seen some property or theorem before and know the proof, then please don't speak it up because other people might be trying it. And yeah, that's basically all I wanted to say. So, all right, this is a buffer problem if anybody wants to take a screenshot. And if you're done with it, just tell me, I'll give you another. Wait, how do I make this larger? Uh, yeah, this is about.
Yeah, yeah, okay.
Okay, so just move it up a bit. Sure. So we'll start with very basics. And I also had a previous lecture that was on miscellaneous geometry, and I did a couple of geometry problems, but I'll be recapping those because most of you are new and probably have not watched that one. Okay, so, and I also encourage everybody to speak up as it'll be difficult for me to check the chat. But, okay. So let's start with the most basic, which is sine rule. So I think everybody knows this one. So it's just if ABC are the sides of a triangle, then AY sine A is BY sine B is CY sine C. And that is equal to twice of the circumference. Uh,
Can you show the problem again?
oh, sure. Okay. Here. Tell me once you're done taking the screenshot.
Okay, done.
All right. So, yeah, there are many proofs of this, but I'll be doing a very clever one. So this is the one that is the least spoken about. Sorry for the bad diagram. Yeah, so this is a triangle, and let's consider the circumcenter O. So we want to prove that A by sine A is equal to 2R because then the others will follow by symmetry. So what we're going to do is we're going to join B and O, and we will drop the perpendicular from O. So can anybody tell me what this angle is? Like you can look at angle BOC first, and then angle BOM. What is angle BOM? In terms of the angles of the triangle. Anyone?
Triangle A only, no?
Yeah, exactly. It's just A. So, all right. So what is sine A in this triangle, triangle BOM? So sine A is, wait a second. It's height by hypotenuse, so it's BM by BO. BM by BO. And BM is just half of A, right? So it's A by 2 and BO is just R. So we got that A by sine A is 2R. So the others follow by symmetry. So we are done with the proof. Next, we should move on to the second most popular theorem, which is cosine rule. So if ABC is a triangle, then cos of any angle is b squared plus c squared minus a squared. Can anybody tell me how the proof goes? So again, there are many approaches, so anyone. Anybody?
I mean, looks like Pythagoras is involved somehow.
Uh, yes. Okay. Right. You say that because you see the squares. Is that it?
Yeah.
Okay. Sure. So, like, there's a proof using Pythagoras, and it'll be very long, so you can look it up. But we'll be doing something that's a bit more clever. So, what we're going to prove is that, okay, how do I go about this? So, I want to find this length BC. So, BC is simply equal to BD plus DC, right? And if you have studied a bit of trig, then you know that there's something called the projection formula. And this side is C, this is B, and this is B. So BD is just equal to C cos B, right? Yeah, C cos B. So BD is equal to C cos B. Do you see why that is? Because cos B is just BD by AC. Therefore, BD is C cos B. And similarly, DC is B cos C. So we can just do that, and we can write it as B cos C plus C cos B. Yeah, fine. Now we want to compute something which is going to be, well, a squared minus b squared. Did we want to do that? One second. So, sure. So we want to compute c squared minus b squared. So do you see that c squared is ad squared plus bd squared and b squared is ad squared plus dc squared? So c squared minus b squared is simply equal to bd squared minus dc squared because the ad squared in there cancels. So this is bd squared minus dc squared. So we can write it as bd plus dc into bd minus dc. And bd plus dc is simply equal to a, right? And bd minus dc, we can write it as bd plus dc minus 2dc. So that is a minus twice of dc. And we know the value of dc, right? It's b cos c. So we can replace that. So it's a times a minus 2b cos c. Sorry, this should have been capital. But anyway. And that means it's a squared minus 2bc cos 2ab, sorry. Square minus 2ab cos c. So we can get the original thing that we wanted just by rearranging the terms. So do you see why that follows? Is this clear?
But like, why we need to find c square minus b square?
Because, okay, this is because like we want to involve the squares of the length somehow, right? So, I mean, how do I explain this? Okay, fair. We want to involve the squares of these, and we want to involve BD and DC because BD and DC are known lengths. So, like, it is pretty natural to find C square minus B square, right? Okay, have I done the computation correctly? Let me check once. So, what would this give me? Wait a sec. Cos C is just A square plus B square. Wait. Yeah, this is right? Yeah. C square by 2AB. So we get cos C from here, and this should be analogous. So just what we proved essentially wasn't cos A, but it was cos C. So yeah, I should have mentioned that before, my bad. And cos C is supposed to be b square plus a square minus c square by 2ab. And that's what we found out. So when we are trying to find out cos C, okay, this is a good question now, because we have that DC is cos C, and we want to involve c squared and b squared somehow. And there's b squared minus c squared. The term is in this. So, like, we can rearrange this to write it as b squared minus c squared equals 2ab cos c minus a squared. So, finding b squared minus c squared or c squared minus b squared is pretty natural because we know that AD will cancel off by Pythagoras, and these two lengths are known, and we know them by cos of the angles. So that is basically the motivation behind looking at c squared minus b squared. Does it make sense?
Yes, but is there any proof in which we don't consider the formula before? Like we directly originate the formula.
Like without using, okay, we are not using cosine rule here before. We are just using that cos of an angle is base by hypotenuse. So here cos B is just like BD by C. And from that we get that BD is C cos B. So essentially we are not using the formula of cosine rule here before. This is like not a cyclic proof. So yeah, this is one approach, and you can find other proofs of the cosine rule using just like Pythagoras. So one sec, I'll just figure that out. How should I go about this? Uh, there. I think you could look at the altitudes of the triangle. Okay, one second. I will demonstrate a proof using just Pythagoras a bit later after we start doing problems. Is that fine? I'll have
Yes.
to look at it as well. Sure. So now the burning question that why do we want to do trig? Why not synthetic? Because trig has two like good things apart from the bad ones. So the first one is we can do clever substitutions, and that is something which is pretty interesting because substitutions make the job a lot easier. And we can work with parameters and we can substitute stuff. But the bad thing about trig is that we have to do a lot of computation. So, I mean, it's worth the pain, but yeah, sure. So that's why we would love to do trig, because when we're not getting any synthetic ideas and we are like basically stuck on the problem and there are a lot of angles and sides given to us, then it's better to just, manipulate stuff and find parameters and make good substitutions. Yeah, that's basically all I have to say. And if you're in 11th or 12th, then you must know these stuff. So it'll be repetitive. So you can try the buffer problems. But most of the people don't know these stuff yet, I guess. So there are a couple of formulas that are known as addition formulas and the like product to sum to product. So I'm just quickly going to write this down. So the first one is that sine A plus B is sine A cos B plus cos A sine B. And the reason I have a plus minus written here is that if I'm taking sine of A minus B, then it's just sine A cos B minus cos A sine B. So yeah, somebody asks what the buffer problem is. So yeah, I showed it in the beginning. This is the buffer prop. You can take a screenshot. And yeah, please feel free to unmute and speak, please. I might not check chat.
Yes, thanks.
Okay. All right. So this is the addition formula that we are all very familiar with. Then the next one is cos A plus minus B is cos A cos B minus plus sin A sin B. And the third one and the last one is tan A plus minus B is tan A plus minus tan B by 1 minus plus tan A tan B. And you can derive analogous formulas for sec, cos, and cosec, but they are like rarely used. I personally have never seen a problem that uses those. So yeah, you can just ignore them or whatever. Just replace one by sine, one by cos. Whatever. So the multiple angles is not necessarily an important thing to remember. So whenever you see some 2x, 2 theta pop up, just think that it's sine x plus x. So it is just 2 sine x cos x. And I would encourage you to remember the formulae for sine 2 theta and cos 2 theta. But like 3 theta, 4 theta is just insane. So never remember that. You can always write n theta as theta plus n minus 1 theta and then break it down. Then you break the n minus 1 thetas all over. It'll be lengthy, but it's worth doing that instead of remembering stuff. So sine 2 theta and cos 2 theta are always going to come off all the time. So yeah, I mean, it's just easy to remember them rather than to write. So cos 2 theta is, yeah, it's cos square x minus sine square x. And notice that you can write this as 2 cos square x minus 1 and also 1 minus 2 sine square x. So that is also an advantage when you want something like cos 2 theta minus 1 or 1 minus cos 2 theta. So you get a perfect square. That's cool. And the third one that you should remember is tan 2 theta because it's 2 tan theta. Okay, I should say x by 1 minus tan square. So these are the multiple angles essentially. I am just not going to write down the 3 theta, 4 theta. So just don't even think about it. So the next one is sum to product. And okay, these are annoying and just best to memorize. Yeah. The sine x plus sine y is equal to 2 sine x plus y by 2 cos x minus. And sine x minus sine y is 2 sine x minus y by 2 cos plus y by 2. Yeah. Okay, then cos x plus cos y. Does anybody have any progress on the buff problem, by the way? Do you want hints? Cos by
Think
2.
you can give us some time.
All right, sure. Minus y by 2 and cos x minus cos y. So I agree that these are very annoying and I still have to derive it sometimes. So just then do it however you want to do it. Another thing is that like to remember when something is sine or when it is cos, when both are sine, both are cos, it always helps to check some like very trivial values. Like you can put 0, 30, 0, 60, 0, 0 or whatever and check like because if both are cos, then both will be 1 and all. So yeah, I mean, it's always good to check
On the
trivial
last one,
values.
is it minus 2?
Yeah, it's minus 2.
How
That
do we
one.
derive this?
Okay, so deriving these is, okay, that's a good question. So these formulae, like sine A plus B is sine A cos B plus cos A sine B. So we derive these by using the addition formulae. So basically what you're going to do is just write down this sine A plus B plus sine A minus B. And what is this going to be? 2 sine A cos B, right? Because the cos of sine B cancels. And now the thing that you can do is substitute A plus B to be C and A minus B to be D. And then you can solve for C and D and you will get C and D in terms of A. And or like you can just get A and B in terms of C and D. That is what we want. So if you do that, then you'll get sine C plus sine D's formula in terms of like 2 sine something, cos something. And if you like solve for A and B in terms of C and D, this is going to be equal to c plus d by 2. This is very easy. You can just check it in a minute. And b is going to be equal to c minus d by 2. So that's essentially the way we derive it. Is that
Understood.
clear? Yeah. And okay, so before writing the product to sum, I'll just say how we derive it because you just asked. So it's simply the opposite of sum product. So if we have sine A cos B, always think that sine A plus sine B was sine A cos B minus cos A sine B, or sine A cos B plus cos A sine B. So whenever we want sine A cos B, we will subtract two sines. So product to sum is just that we will be given something like sine A sine B, and that is just half of cos A minus B minus cos A plus B. So yeah, this is just straightforward. Why is my stylus behaving so weird? Anyway, yeah. So you can see here that like sine A cos B is this. So if we did sine A sine B, for example, then we would have to take cos A minus B minus cos A plus B. This is a proof of that. So like this is going to be twice sine A sine B. And from here, you can get sine A sine B is half of cos A minus B minus cos A plus B. Is this clear?
Yes.
Okay. So similarly, like cos A cos B is half of cos A plus B. And if you're not convinced, if somebody is not convinced with these, I would suggest just computing the sum to products and then making the suitable substitutions and then finding the product to sums, or just using the addition formulae to do the sum to products. Like that helps. That helps to be convinced that these do work. Anyway, so this is the cos A cos B. Third one is sine A cos B. And yeah, this is half sine A plus B plus sine A minus. And cos A sine B is exactly the same, just flip the names, right? Like cos A sine B is the same as sine A cos B. I think you understand why. So that's it for the annoying formulae. So we are just going to do some other formulas which are not as computational, but okay, they are pretty important and come up very often. So the first one is that I'll number these. And remind me to change the color because it comes monotonous quite often. Anyway, so the first formula we're going to do is small r. So I'm claiming that this is equal to s minus a times tan a by 2. This is very, very easy to see. So I'll just tell you how to see it. So take the triangle, take the in center, and drop this perpendicular. So this is your small r, and if this is the tangential circle, then this is s minus a. And this angle is a by 2 because it's the in center. So this is a by 2. So tangent of a by 2 is equal to r by s minus. So yeah, r is s minus a times tangent of a by 2. Done. All right. So the second thing is that what should I go over next? Well, fine. Okay, the next one is r is delta by s. This is not something I really want to show using trig. So just this is for FYI, you know. And the second thing I'm claiming is that this is 4r sine a by 2, sine b by 2, sine c by 2. So I'm going to give you 5 minutes to think about this because this is very important and it's going to come up pretty often in some stuff we are going to prove. So best to think about it for a while before I spoil it.
R is in radius, no?
Yeah, R is the in radius, small r is the in radius, and capital R is the circumradius. And please feel free to speak up if you have any ideas. Doesn't have to be correct all the time.
The delta has a representation with like sine A and something else, right? There was a
Uh,
area formula for triangle, I think, like that.
which one?
And those terms, something like that.
Area formula for triangles. So that is,
Yeah.
are you talking about
It
half
was,
AB sine A? Half BC sine A.
yes, yes, something like that.
Okay.
We try to substitute that and then break the sine b by 2 and c by 2 using the sum formula.
Okay.
Product is,
That's
then,
that's a very good idea. Yes.
and then we get like sine whatever 180 minus a or something and you do stuff with that.
Okay, but if you're trying to replace this, then you will get A, but not A by 2, right? And if you want to convert it into A by 2, you will get 2 sine A by 2 cos A by 2. How are you going to deal with that?
You could use Pythagoras, but then that's just bad.
Uh,
Like you don't want
Pythagoras
sine
for
square, right? No, no, the
cos A by,
Pythagoras sine square
yeah.
equals cos square, right? I think. But then that's
Okay.
just bad.
Okay. I see what you're trying to say. Fair. All right. So sure, that works. So while you're working on this, just try to do this once as well. These half angle identities are often useful. So I'll come to the proof of this in a while. So try to prove these. So sine of A by 2 is S minus B times S minus C. I think many of you should have seen this, but just try to think about it for a while. Cos A by 2 is S minus A by BC. I mean, if you have the sine, then it's very easy to get the cos because like just do a root over 1 minus sine square. So it's enough to just prove this and we get this automatically. So try to prove this for a while. And if you have any ideas, let me know.
Is 27 the answer for the upper problem I gave earlier?
Uh, What did you say the answer was?
27.
Sorry, it's 69.
Also, for the second identity that you were doing,
Yes?
so when we take like sine b by 2, sine c by 2, there'll be
Yes?
a cos formula, right? There'll be a cos term there of cos 180 minus a by 2 that will get formed, right?
Oh, yes. Okay.
So when you multiply that with sine a by 2, we already have a factor of 4. So that's 2 sine a by 2 cos a by 2. So sine a by a gets created there as well,
Yes.
right?
Yeah. Okay, could you repeat that? I should write it down.
Yeah,
Okay, you
I'm trying to first show that delta by s is equal to the 4r thing.
exactly. Okay.
What I'm doing is I'm substituting delta with 1 by 2 sine a bc.
Okay. Yeah.
And then in the RHS, we look at sine b by 2, sine c by 2.
Yeah. Okay.
So when we'll take a factor of 2 from the 4.
Yes,
So then,
exactly.
yeah, and
2
then
sine
you,
b by 2 sine c by 2, right? And you
yeah,
do product to sum.
yeah, product is up.
Exactly. Okay, that's
And
how you're
then,
going to go about it.
yeah, and then after doing product to sum, you'll get,
A
um,
180 minus thing, exactly. That's
yeah,
what you said. Yeah.
yeah. And
And
then
that's
you'll
just
get
going
like
to
a
cancel
sine,
out.
right? Yeah, you'll get a sine, and then you can probably do some stuff as well using
Yes.
cosine formula later
Yes. Uh-huh.
because it's a easy there, right?
Yeah, that's exactly the way to go about this. So I
Yeah.
won't spoiler everything because people aren't like speaking up a lot. So, well, I'll just say that there's also a way that you can go from 3 to 2, and that's by using cos a by 2, this one. So, okay, I'll just tell you how to get from 3 to 2, and I'm not going to tell you the individual proofs for 2 and 3. So you can try this one on your own. Try to prove 2 and try to prove 3. So these are pretty useful, and yeah, you can find some problems that use this. So I will just show you how to go from 3 to 2. So you'll see how powerful this stuff actually is. So cos a by 2 from 3 is square root ss minus a by bc. I actually need more space to do this. Can I use space? Hopefully can. Wait. Um, yeah, okay, fair. All right. So we get cos a by 2 is this. And okay, we don't want cos a by 2. If you really wanted to do it by cos a by 2, you would replace sine a's with 2 sine a by 2 cos a by 2, but that's really not necessary. So by this formula, sine a by 2 sine b by 2 sine c by 2 is simply like you will multiply s minus b, s minus c, and then s minus a. So I'll tell you the way it goes. There's a square root, and s minus b comes twice, s minus c comes twice, and s minus a comes. Okay, I'll just rigorously do it. It's not nice to handle everything. Sine a by 2, sine b by 2. Sine C. So what you're going to get is a very big square root and s minus a whole square in the numerator, then s minus b whole square, then s minus c whole square. Do you see where the whole squares come in? I mean, okay, I'll take that as a yes. So this is s minus a, s minus b, s minus. And do you see that this is absolutely like Heron's formula? So, oh, sorry, the whole square there. All right. So this is just delta squared by s squared ABC. And I think you remember this formula. Delta equal to ABC by 4R. So what is ABC? 4R times delta, right? So it is delta squared by S 4r times there's a delta. Yes. So the delta cancels. And if you take 4r to the other side, you just get that delta by s is 4r sine a by 2 sine b by 2 sine c by 2. And you just land up with this formula. So it's pretty easy to get from 3 to 2. But this is a challenge to prove 3 and 2 just without using each other. So that's one of the homeworks. And I'll probably gonna put that on the problem set, but yeah, you can just try it. Anyway. So now we are going to come to something that's really nice. Okay. So oftentimes we have the centers of the triangle involved in our problem, and OHI are involved at like 99% of the problems. So we know these three formulae. OI squared is r square minus 2rr, which is just Euler's formula. I think you've seen this. OH squared is r squared into 1 minus 8 cos A cos B cos C. And IH squared is 2r squared minus 4r squared. So, okay, if you were to take my word, then I would say that these two are easy. And this is pretty hard. So, does anybody know the proof of this? Or like, okay, there's one question I want to ask. Would you like to do the proofs of this if I just tell you the idea? Or do you want me to prove like one of them?
I think for the OI formula, there was some power of a point thing you could do. I had seen the proofs of this a while back.
Yes, absolutely. So like OI square is the easiest, of course. And there's a power of a point argument, like you said. But what if we want to prove it entirely by trig? So I think you guys are not familiar with this. So I'll just show you the computation of OI. I'm going to, okay, I'll just tell you how you can approach it. All right. So you are going to consider the triangle ABC, and then you're going to consider the points O and I. O is somewhere here, I is somewhere here. Okay? And now look at the triangle AOI. So can anybody tell me what angle IAO is? So I want to find angle IAO.
I guess you can just take angle IAC as A by 2 and then minus angle OAC, which is 90 minus
Yes.
B.
Okay. All right. People speak up, and thank you, Shreya. So this is IAC minus OAC, and IAC is just A by 2, and OAC is 90 minus B by 2. What? 90 minus B. Sorry. It's not B. Fair. Or you could also do this, which is like OAB minus IAB. So like just for convenience, let's do that. I mean, both ways are fine. So it is, and OAB is 90 minus C, and this is IAB is A by 2. So it's A by 2. So this is angle IAO. And why did I want to compute IAO? That's the obvious question. And this is nice because I know that IA is S minus A tan A by 2, if you remember. Like IA. Oh, sorry. I don't know IA. Right. Why is my screen frozen? Yeah, sure. So I know that R is this and okay, did we find out R? Okay, we find out R, which is S minus A tan A by 2. And we can just find out IA from that triangle because it's a right triangle and a right triangle is nice for trig. So we basically know IA because this is the right triangle we can consider. And we also know AO. So we know stuff from triangle AOI, and we also know this angle. So let me highlight what we know. We know AI, we know AO is just simply capital R or the circumradius, and we know this angle. So what does this remind you of? What should we do to find out IO? It's one of the first things. Exactly. Let's do cosine rule. So from that we can get OI squared is going to be AO squared plus AI squared. Oh my God, this is really bad. AI squared minus twice AO AI cos 90 minus C minus A. This is just the IAO found out. And this is just R squared plus AI squared minus 2R AI. And notice you can write cos of 90 minus C minus A by 2 as sine of A by 2 plus C. Is that clear, or should I go about it? Because just cos of 90 minus theta is sine theta, right? So this is sine of C plus A by 2. I mean, there's nothing to explain. Is this clear? Is it clear up to this?
Yes.
All right. So we want to prove that this is equal to R squared minus 2R, obvious formula. So the next step would be to find out AI. Look, I need even more space. Fine. So we want to find out AI. And notice that in this tiny triangle, this is R, A, and I. So AI is going to be, damn. Okay. This is going to be R by sine A by 2. Just compute sine A by 2 and you'll get that it's R by sine A by 2. And by the formula that we just saw right now, R was 4R sine A by 2, sine B by 2, sine C by 2. The sine B by 2 and sine C by 2 cancel. So it is 4R sine B by 2. Okay, I said that wrong. Sine B by 2 and C by 2 don't cancel. Sine A by 2 just cancels with the denominator. So it's sine B by 2, sine C by 2. So we found out AI. So basically, what is AI squared? It is, now for AI squared, we will multiply this and this together and not square any one of them. Why? Because for AI squared, we somehow want a 2RR because we have a 2RR in here. So we can take okay, these two are equal. So we want to equal these two. So we want to take a factor of 2RR out of this. And we want a 2R small r. So in this AI, we are going to replace this formula. And for this AI squared, we are going to multiply both the formulae together. So what do we get? It is like 4RR sine B by 2 sine C by 2 by sine A by 2. Okay. And okay, so we are not trying to find out AI square at this point. Let me just do colors. So let's find out this entire thing because that is going to be very convenient. So this green is equal to this thing minus 2RR sine A by 2 plus C by sine A by 2. Do you see why that happens? Let me zoom out. Is everything up till this point clear to everyone? Okay, I'll take that as a yes. So it'll be really nice if you speak up. anyway. So that means what are we reduced to show? We are reduced to show that this 2RR and from here we'll get a 2RR somehow. And we want to show that it's equal to 2RR. So what are we just reduced to showing? We are reduced to showing that sine A by 2 plus C by sine A by 2 is not equal to minus 2 sine B by 2. Okay, this is very, very bad. B by 2 sine C by 2 by sine A by 2 is equal to 1. So this is what we want to show, right? And this means we are reduced to showing that sine A by 2 plus C. And now we're going to do something clever. So we'll take the A by 2 and multiply it out here. So we will take this A by 2, cancel them, and multiply it out here, sine A by 2. We'll bring this A by 2 to this side and this to this side. So what do we finally have? We have, okay, that was this one. Yeah, minus sine A by 2 is equal to 2 sine B by 2 sine C by 2. And what is this? Isn't this obvious? Okay, apparently not. But I mean, sure, we just did sum to product, right? So sine A minus sine B is what? 2 sine A plus B by 2 sine A minus B by 2. What is A plus B? A plus B is just A plus C here for this particular thing. And A plus C is 180 minus B. And we are going to do that by 2, right? So what do we get? Sine B by 2. And the second term is going to be A minus B by 2. What is this minus this? It is just C. So we have a C by 2. So it's sine C by 2 here. So is this clear? Like people are not speaking up.
Yes, it's not.
All right, sure. So that's how we prove that, okay, we are done, right? Because we wanted to show that this is equal to 1. So we can just go backwards and we are done proving that y squared is r squared minus 2r. All right. So, okay, I have two options. Basically, I wanted to do a bit of more theory, but this took me quite a lot of time. So do you want to do some more theory or do you want to switch to problems? Because there's like no hardcore trigonometry theory left. It's all like application based. And the other option I have is do a couple problems. So what do you want to do?
I think problems are good.
All right. Okay. I was thinking the same. So this is the first problem that we're going to do. So I'll give you 5 minutes to read this and try. Let me know if you have any progress. And feel free to DM me at this point because like I understand if it's hard for you to speak. I'll just be drawing the diagram in the meantime. So if you don't want spoilers, just don't.
Uh, addition. Uh,
Sorry. All right. Does anybody have ideas? It's been quite long.
I think just angle chasing.
Sure. And how would you do that? Because angle chasing
So,
does not seem to work.
Okay, so angle,
Yes.
so ADC, we know ADC, right? Which is 105.
Yeah. ADC is 105. Yeah.
Yeah. Wait, let me just think about it.
Okay. I won't spoiler it, but can you look at the angles in this figure and try to find out how this happened? Like how these angles came out to be these?
I guess we have to construct something and make a cyclic quadrilateral.
Okay. Which one would you want to do? Like what construction?
I'm not sure, but I think cyclic quadrilaterals might help.
Okay. It's a good idea. Any other ideas? Cool. So I think I should go with this. Like, should not take so much time. It's pretty easy. Anyway, before doing the trig one, let me just do the synthetic one because some of you were talking about constructions. So, all right. So what we're going to do is we are going to consider the incenter of ABD. So let's call this to be I, the incenter of ABD. So I is incenter ABD. Yeah. And like, okay, my diagram is very bad, but what should happen is that since AC bisects like angle A, I should lie on AC, right? So let me draw it accordingly. Please don't mind my diagram because it's pretty messy. Yeah, this is I, whatever. So I belongs to AC. And like we want to find DIB first of all. So what is DIB? DIB is 90 plus 55. Oh my God, stop this. Okay, so that is 145. So that is the first hint. So do you see something? This angle is 145. Do you see any other angle that will form a cyclic chord?
Yeah, angle C.
Angle C, yes. So
Actually,
IDC,
CD,
sorry?
nothing. I was just saying that
Okay,
PCD
sure.
is
Cyclic, yes. So the next thing we want to find out is angle IBD. So IBD is obviously 20 degrees, right? IBD is 20 degrees. Okay. So does anybody have any idea what should we do next? I'll just write my walkthrough. Okay, what do you want to find out?
IBD is angle B by 2. So, I mean
IBD,
ABD by 2.
exactly. Done. So BI is the angle bisector of angle B. So IBD is just B by 2 or ABD by 2. And so we have that angle. So angle ABD by 2, which gives us angle ABD is 40 degrees. Okay, that was solution 1. What is solution 2, the intended one? What is trig? Like anybody, any ideas on trig approach? Sorry, I was on mute. So yeah, I'll just get you started on the trig approach.
Wait, can we have a minute?
Do you want me to wait?
Yes.
All right, sure. Tell me once you're done, huh? Are you done? Also, is
Yes, you
anybody
can
else
start. You
trying?
can start.
Okay, sure. So the first thing we want to do is let's do sine rule on ADC. So what do we get? We get AD by sine 20 is equal to AC by sine 105. Okay. And now we are going to do sine rule on ABC. So AB by sine 15. Oh my God, sorry. Sine 15 is AC by sine 1, 1, 0. So we can just divide these two, right? So we will get AD by sine 20 into sine 105. Or you can think about it like this. Just equate ABC from both the equations. Is AB by sine 15 sine 1, 1, 0. Okay. So from this, you'll get that AD by AB is what? Sine 20 sine 1, 1, 0 by sine 15 sine 1. Yeah. Does that make sense? Is that fine?
Yes.
Okay. Also, by sine rule in ABD, what can you say AD by AB is?
Sine B upon sine D.
It's the opposite.
Yeah.
Sine alpha by sine 70 minus alpha. Yes, exactly. So, do you have any ideas how we can move forward from this?
So sine 110 is like sine 180 minus 70. And so you generate like a cos 70 or something from there. Wait,
Cos,
what is
it's
sine
still sine
180?
70.
Yeah, it's still sine 70, right?
Yes.
Yeah. Can't you just brute force this? I mean, you
Yes,
have
we have to
time.
brute force this.
Yeah.
Yeah. So, I mean, we have sine 15, sine 105, and sine 20, sine 110. So, what these two have in common is that 105 minus 15 is 90, and 70 plus 20 is 90. So, the 90 terms just go away, right? And it's cos 90 for that matter. So, cos 90 just goes away. So, we can just convert this into like product to sum, and we'll get a head start. Does that make sense? Okay, I'll just do the product sum. So sine 20 sine 70 is equal to like, what is it? Cosine. Uh, I mean, let's just keep it this way, okay? We are just getting it from this. So what is it? 90, right? 30. Yeah. This is cos 90 minus cos 130. Can you check, please? This is cos 90 minus cos 120 is fine. Hold on. Sine 20, sine 110, and to sine alpha cos alpha is cos alpha minus beta minus cos alpha plus beta. Yeah. So, yeah, this seems to be correct, right? Yeah, this is right. Okay. So, cos 90 is 0. So, this is just cos 130 by cos 120. So what is cos 130? It is just sine of what? Sine of 40, right? Yes, it's sine 40. And this is sine 30. So okay, fine, fair. And what did we have like in the beginning? We had that this is equal to, let me change the color. This is all right. Yeah, this is equal to sine alpha by sine 70 minus alpha. So like now you can sort of cross multiply and then do product like product to sum and then sort of brute force and then you'll get that alpha is equal to 40 degrees. Can you do that computation by yourself or should I? Yeah, it's just clear from here, right? But there are some inadvertent cases that we want to look out for. So alpha is 40. We just need to cross multiply and do it. So is that clear? Okay. So I think you can do that part by yourself. So we got that alpha is what 40 degrees and we wanted alpha. ABD was our required thing. So the answer is 40. Anyway, this stuff is pretty hard for IOQM. So if you're not getting it, please don't be discouraged because this is not IOQM stuff and this is just trig in general. Yeah. So the next problem, here's the next problem. Do we have time actually? What should we do? Yeah. Okay, this is fine. Okay, I'll just also tell you the source. This is the what? this is the first problem of chapter 11 of EGMO. So if you've done it, then please skip off the problem.
Isn't chapter 11 spice? Oh no, it's the any problems, miscellaneous.
Yeah, it's a personal favorite.
And can you go down a bit? Yeah, that works.
Okay, so wow, somebody pointed out to me that we can make the trig solution a bit shorter, and this is actually nice because okay, obviously the trig solution doesn't involve the incenter. By the way, am I audible?
Yes.
Yeah.
Okay, sorry. Okay, so the trig solution doesn't use the incenter, and this also doesn't use the incenter. So I think all of you know about trig keva, which is like if you have a triangle, three concurring serients, and these angles are like alpha, beta, gamma, delta. Oh, sorry, this is phi. It's delta, phi, and what? Psi or something. So like sine alpha by sine beta times sine gamma by sine delta times sine phi by sine psi is 1. This is trig keva. Is everybody familiar?
Yeah.
Okay, so uh, you could look at triangle BCD at this point and consider your serients to be like BA, CA, and DA. So the angles are nice because I know 20, I know 15, and one of the angles is alpha, like with BC, one of the angles is alpha, the other one is angle B, which is 110. And with angle D, one of the angles is 70 minus alpha, and the other one is angle D, which is 105. And what I essentially wrote down here, this big thing, was nothing but the trig keva for like BCD. So if you modify that a little, you'll just get the trig keva. So that's also another approach you could try. Yeah. Okay, let's move on to this one. Like you
What
could
are the CVMs and in which triangle?
all right, hold on. So triangle is BCD, and the CVNs are AC, AB, and AD. They concur at A, right? So we can do trig keva.
Okay.
Yeah, that's all. Anybody, any thoughts about 11.1 or like second problem?
You have to show the kite, right?
Yeah. Okay, so 11.1 is like this. So if you have a triangle, three concurring serients, and these angles are 70 minus alpha, the other one is angle B, which is 105. And what I essentially wrote down here, this big thing, was nothing but the trig keva for like BCD. So if you modify that a little, you'll just get the trig keva. So This problem is actually nice because it has like a very short synthetic solution. I'll be giving you a few more minutes. Try to get it done.
I think I got the synthetic solution.
All right, go on.
Yeah, so you draw ABCD
Oh,
and
okay.
you take the intersections of AB and CD to be something.
All right, A, B, and C. A, B, and C, D. So
Can you actually take it to be convex? Yes.
what? X.
You know, the angles won't make sense here, huh?
The angles would make sense actually.
No,
Right.
one of the angles has to be greater than 180, right?
Yeah, I mean, what? No, 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 no. It's convex.
Oh, wait, right. What am I doing? Oh, sorry about that.
No props. Okay, so I'll give you a pointer for the synthetic solution. Just consider these two. Okay, I need a diagram. What am I doing with my diagram? Just murdering every time. So what I basically want to consider is the intersection of the extended sides. So yeah, I'll just make a better diagram. This should work out. Yeah, this is A. Sorry, this is not A. This is B. A, B, C, and D, right? So the things I wanted to consider for the synthetic solution is this intersection. Let's call it some F, and this intersection, let's call it some E. All right. So now look at the angles. So what are we given? We're given that CBD is twice of ADB. So if this is 2 beta, this is beta. And if this is like ABD, right? This is 2 alpha, then this is alpha. And AB is equal to CD. So now look at the angles. Look at every angle, compute every angle.
Yeah, I think you get congruence, right?
Exactly. And the congruence is not very non-trivial, it's pretty trivial because these two are equal, vertically opposite. And well, what do we do actually? This angle, what was it? It's twice of alpha plus beta. Okay, it's not match.
I think I got the Pridhw's solution.
You got the, sorry?
Pridwas solution of this.
The best solution. All right. Okay. How are you going about this?
So can I first complete the synthetic one and then we can move
Okay, sure. It's all right.
on? Yeah, so
So,
it's AEB in terms of alpha and beta.
and what is it?
180 minus alpha minus beta. Right.
AEB.
Yeah. E is the intersection of BC and AE, right? BC and
AD.
AD. Right?
Yes. So it's not
Yeah.
180 minus something, right? You look at this triangle. Wait. You look at this triangle, and this is an extended side. So do exterior angles. This is 2 beta. This is beta. Then what is this?
Wait, can't you apply angle sum on triangle ABD?
ABD. I mean, what are you trying to find out? Did I misunderstand?
So we're looking at congruence between EAB and FBC, right?
Okay, sure.
So I'm just trying to compute angle E and angle F in terms of
Oh,
alpha and beta.
okay. So sorry, I thought that you were trying to figure out this and this directly, but sure. So you're doing angle sum here. So it is 180 minus 2 alpha plus beta, right? And this is 2 alpha plus beta.
Yeah.
Then what you're doing?
And then you get angle E, right? You basically
Yes.
get angle.
So angle E is angle
But
B,
again,
right?
angle
Because
sum.
it's
Do the same. Yeah. And then you do the same thing with angle
yes.
F, and then you should get congruence.
So all right, this is fine. But like a shorter way to do this is like not to do angle sum first of all. So what you would do is that look at triangle BED. So this is angle beta, and this is 2 beta. It's exterior. So it's directly beta. Like we don't need angle sum. And this angle, this is twice alpha. This is alpha. So this is also alpha, right? And we have that these two sides are equal. And these angles are equal by vertically opposite. So what should we do for the third congruence thing? Because we don't know that alpha and beta are equal, right?
Just AB equal to BC.
AB equal to BC. These two angles are equal. And what? What's the third?
No, you're given that AB is equal to BC, right? So you can use AAS criteria for something.
What are the angles? Okay, wait. There's some misunderstanding. AB equal to BC. Then angle EBA equal to angle FBC. What's the third? So this is actually pretty trivial because look at triangle BED.
Oh, right.
Yeah, it's
Yeah,
isosceles.
yeah.
So EB is equal to BD and BD is in turn equal to BF. So we get that the third condition is that, why am I writing so bad today? EB equals FB. So we get that these two triangles are congruent, and therefore by CPCT, alpha is beta. So done, right? AD equals CD. Because if alpha equals beta, then ABD and CBD are also congruent. Does that make sense?
Yeah.
Okay. So we have very little time left. So let's move on to the bash. Somebody said that you were done with the bash. Do you want to say your solution?
It's like basically, first I will apply sample triangle ABD.
Yes.
like I will apply sine triangle ABD, and
Mhm.
like I will get that AB by sine beta is
Yeah.
equal to BD by 2 sine or 2 alpha plus beta.
Sine 2 alpha plus beta.
Yeah, and similarly, I will get a BC by sine alpha
Yeah.
is equal to um, BD by sine 2 alpha or BD by sine 2 beta plus alpha.
Exactly. Mhm.
So like I will equate as AB is equal to BC, I will equate both. Like I will equate both, and like I will get that sine
Mm.
beta by sine alpha is equal to sine 2 alpha sine 2 alpha plus beta by sine 2 beta plus alpha.
Yes, exactly.
And like I will take write this as sine beta times sine 2 beta plus alpha is equal to sine 2 alpha plus beta times sine alpha, and like I will like use the identity of sine A, sine B to get that cos
You
of
cross
3.
multiply, right?
Yeah,
Yeah. Okay. Cross multiply and then make it sine like product to sum, and then cos 3 beta plus alpha is cos 3 alpha plus beta, right?
yeah, and like you will get cos 3 alpha plus beta is equal to
Cos 3 beta plus alpha. Right?
yeah.
Exactly. That's perfect. That's absolutely perfect. But you can't directly compute that 3 beta plus alpha is equal to 3 alpha plus beta. I'll come to that. 1 second. But is everybody clear till this step? This is the main thing of the problem. Like, there's absolutely nothing else.
Yeah, it's clear.
Okay. So, like, when is cos A equal to cos B? So, there are two conditions when, like, um, okay, the first one is A equal to B, like, and the second one is that A plus B is 360. Like, you can get this from the graph of cos, because, like, what is the graph of cos like? Is it around? Yeah, it starts from 1, right? Yeah, something like this. Yeah. So one condition is that like it can be equal in this way, and the other one is that it can be equal to in this way, right? So like either these two are equal or their sum is 360. So that's basically the cost thing. But we can say that their sum, look, okay, let's see what their sum is. So it's 3 beta plus alpha plus 3 alpha plus. Okay, is it 360? I don't think it's 360, it's 180. Yeah, is it? Yeah, it's 180. Sorry. Okay, that's my bad. Okay.
No, I think it's I think if cos A plus cos B is equal to cos A plus cos A is equal to cos B, then A plus B should be 360.
360, right? Yes. Sorry. Okay, I get confused a bit.
Yeah,
But yeah.
give it with alpha plus beta is equal to 90.
Uh-huh. So like this is equal to 360, and that means what is alpha plus beta? 90.
Yeah, like you can substitute.
And that means twice alpha plus beta is 180. But remember that we were given, okay, somebody was getting an angle should be 180, right? And we were given that it's convex. And angle B is twice of alpha plus beta. And it can't be 180. It has to be less than 180. And twice of alpha plus beta is exactly angle B. So this case is not possible. So the only remaining case is when 3 beta plus alpha equals 3 alpha plus beta. And that is the case when alpha equals beta. So we just get the same thing, and by conference we can conclude that. Like our earlier conclusion will just follow by conference, right? So we will get that AD equals BC. Is this problem clear to everyone? These problems were both pretty easy, and I demonstrated the synthetic as well to like for the sake of completeness. So is everything clear?
Yeah.
All right. Okay. So I actually had planned to do one more problem. This problem is pretty nice. And I also wanted to cover a few more stuff like trig Geva, isogonal conjugates, and Jacobi's theorem using trigonometry. Well, basically, everybody said that they know trig Geva. And isogonal conjugates is just that, like, if you have a point P and you take these, then if you take the like lines such that this angle equals this, then this angle equals this, and this angle equals this. Isogonal conjugate that just means that these three lines also concur if we started with an initial point P. So this just follows by trig Keva because we can just revert that stuff. Like anyway, this is too hand wavy because we are out of time. Okay. Does somebody have an alternative solution? Okay, sure. Can you please? I would love to hear that.
So we join AC and reflect the triangle ABC
Okay, sure.
with respect to AC.
All right.
So let's say the B comes to B dash.
Okay.
So now we claim that B dash is the circumcenter of triangle ADC.
Okay.
Because angle AB dash C is equal to twice the angle ADC and
Yes.
AB dash is equal to BD dash.
AB dash equal to BD dash. How?
Because AB is equal to BC.
Oh, you mean AB dash equals BC dash. B dash C, right?
Yes.
One sec. So what are you claiming? That it's twice and it's equal. Exactly right. Because if this is center and it has to be twice of it, so it has to lie on the circular arc and there's exactly one point. Yeah, fair. So B dash is the center. And I'll just tell everybody quickly why that is so, because if we have a triangle ABC, and if we have an angle like that is twice of A, we can vary this angle in the circular arc BOC, right? This point can be any point on BOC. And if it is the arc midpoint, then that is the circumcenter. But BO equal to OC, or here AB prime equal to B prime C is what ensures us the arc midpoint, so it is the center. Yeah, go on.
So
That's what you
now,
wanted to say, right? I mean, that was the logic, right?
yeah.
Sure. Okay,
So
go
now
on.
BD dash CD is equal to alpha.
CD is equal to alpha. Yes, perfect.
And so CB dash B will be 2 alpha.
Yes,
And we are
exactly.
given,
We're given.
won't it lie on the BD only?
Sorry,
But you don't know if the reflection lies on BD, do you?
we don't.
So how do you know it's alpha?
Because it's a circumcenter, right?
Yeah, but like it
Oh,
doesn't lie on BD. Like the circumcenter near lie on BD.
uh, if it lied on BD, would it be alpha then as
Yes,
well?
if it
But
lied on BD, it is alpha. If it does not, it is.
okay, we don't know that it lies on BD, right? Because if it lied on BD, then we would be like directly making the claim that this is a kite. Do you see where that fails?
Yeah.
Okay. That's a very good approach. And I think it can be modified into a real solution because you can consider some phantom point argument, like, uh, I don't know. Yeah, if it is a reflection, this is just like random thoughts. You can just produce it so that B D prime is equal to BD or something. And then you can construct this A D prime and D prime C, and then you can try to prove that D prime and D coincide. This is a very good line of thought. So yeah, you can try to do it that way as well. Is that fine? Okay, I see the chat. Fair. All right, so I actually wanted to talk about isogonal conjugates and Jacobi's, like I said, but we are out of time. And I will try to make a problem set for you guys, uh, based on like a few more IOQM and AIME-ish trig problems, as well as some USAMO IMO problems. So yeah, I think that's all I had to say. And I will also send you some notes or like some links based on isogonal conjugates and Jacobi's theorem, so you can read about them. And the trigonometric proofs, I might write that down like myself and send you, or I could send you some other link as well. And if you want the solution to the buffer problem, or if you have any doubts about any problems or any theorems that we did, like feel free to DM me at any point. I will tell you the solution, if not immediately. And do note that I sort of miss my DMs at some point. So if I don't reply within like the first 12 hours, please feel free to ping me again. So yeah, that's all I had to say. I hope you enjoyed the class and hope to see you again.
Thanks for teaching.